Hi there, thanks for joining us yet again. This is Space Nuts. My name is Andrew Dunkley. Great to have your company one more time. Well, hopefully it's more than one more time, but on this occasion. Now, with Fred away, we are doing a series of little specials, and today the focus will be on exoplanets. We've known about them since the early 90s, and since then we have found thousands of them. But what is there to know? I mean, we've got our own planets. Surely that just means everything else around the galaxy is the same. That's probably not true. And we're going to talk about all of it today on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And with us while Fred is away is Jonty Horner, Professor of Astrophysics at the University of Southern Queensland. Hi, Jonty.
Good afternoon. How are you going?
I am quite well, and you?
I can't complain. I'm enjoying us having a public holiday today, which is great. I mean, I'm still off anyway, so it doesn't really matter, but it means I'm taking 1 day's less of sick leave, I guess.
Well,
it's all good.
I'm retired, so public holidays mean nothing to me now. I used to so look forward to having a few days off, or an extra long weekend if they combined the two in April, because we get sometimes get Easter and Anzac Day in April, and if you jam them together, you get a nice free holiday. But it doesn't mean squat to me anymore.
I keep finding it bizarre, at least in Toowoomba. I'm sure this is reproduced everywhere. If the shop's shut for 1 day, the day after is absolutely feral. So last week we had Anzac Day, which tells you how long ago these were recorded, by the way. But yeah, last week we had Anzac Day, and obviously for Anzac Day, quite rightly, the shops, the supermarkets and everything are shut. It's one of the biggest holidays in Australia of the lot of them, but we tend to do our shopping on a Sunday anyway, so it didn't really matter. Went to the shops on the Sunday and it was almost people fighting in the aisles, because heaven forfend that 1 day you don't get food for 1 day, and the shops start running empty of bread, and it's like people buy more when they've had 1 day without the shops being open. It's very, very strange phenomenon.
They panic buy, and there's no toilet paper on the shelves. There's all sorts of stuff.
Well, the best thing about that led us to subscribing to Who Gives a Crap, which apparently started online, and they've been brilliant. We've recommended them to everyone because it works out cheaper than getting it from the supermarket, and they're better quality. I mean, it feels like very much a no-brainer, and we'd never have come across them if it wasn't for COVID and the incredibly smart people of Toowoomba going, oh my God, COVID's happening, we're going to run out of toilet paper. Of all the things for the shops to run out of.
Happened everywhere.
Why toilet paper?
I
mean, COVID my memory was that COVID was something that made things come out of your head, not things that came out anywhere else. So it's not like there would be an expectation it would make you use more.
No.
Bread was fine, eggs were fine, perishables were fine, but toilet paper, I don't understand.
I never got it either, but our shelves were devoid of the stuff. We better get down to business. We're talking exoplanets today, and I did a little bit of research. The first exoplanets were confirmed in 1992. In fact, they suspected they existed before that, but they couldn't prove it. But 1992, they found two planets that were later named Poltergeist and Phobetor.
Yeah.
Phobetor. So they were officially the first two exoplanets, and then the first one that was orbiting a sun-like star was found in 1995. That was 51 Pegasi b.
Yes.
So those were the first few, and of course now we've reached a point where, as at the 30th of April 2026, 6,278 confirmed exoplanets, with another 8,000 waiting to be officially catalogued, I suppose. So we've found a lot of them, and the other thing we've been discovering about finding these things is how very different a lot of solar systems are, and how very different some of the planets are. It's what we always thought was basically the standard for solar systems, which was ours, doesn't appear to be very standard at all.
No, it's an incredible time to have lived through. I think the way I always badge this is we've lived through one of the great scientific revolutions almost without noticing it. And I think it sheds a light into how people would have reacted in previous scientific revolutions, which is that when it's happening in your lifetime, it just happens. So we look back and think that was such a fundamental change. And at the time, it was just Tuesday, and
Yes.
it's like that with exoplanets. I grew up in a world where one of the big science questions was, is the solar system unique? Are there planets around other stars, or are we alone? And there were good reasons for some people to suspect that we might be the only planetary system in the universe. There were kind of, at that time, two broadly competing models of planet formation that could both explain the solar system as we see it to a fair degree. One was what's almost described as the Laplace model, the disk model, which is now what we favour, that has developed a lot since then. But the other was this idea that you had a close encounter between the sun and a protostar that was close enough that the two stars almost collided, and a tongue of material was pulled out of the sun which went on to condense to form the planets. And that was championed by people like Martin Wolfson of York University, among others. At this time, we're talking in the late 80s, it was kind of widely held that Wolfson's suggestion had problems. It was probably not the right solution, but it potentially could be. We'd found a few debris disks, debris around stars, a bit like the asteroid belt around the sun, but much more massive, in the early 80s. And that was kind of hinting that planets could be common, that the disk model could be the one. But at the time I was growing up, and at the time going into the early 90s, you had these two models of planet formation that predicted vastly different outcomes. If the disk model was right, planets would be ubiquitous. Planets would just be the leftovers from star formation. And effectively every star would have planets or close to it. If the encounter model was right, then planetary systems would be exceedingly rare, because to get two stars to come sufficiently close together at just the right speed for that to draw a tongue out and form a planetary system is vanishingly unlikely. So that was arguing that we were effectively the result of a freak encounter. And if that prediction was right, then if that method was right, it would predict that planetary systems were exceedingly rare and that we wouldn't find them. So going into the 90s, you had these two theories that could both explain in broad brushstrokes what we see at home, but that predicted very, very, very different outcomes. And as I say, the Wolfson idea was already losing a bit of steam. But in the time since, we found that planets are around other stars and that they are ubiquitous. That basically every star you see in the night sky, no matter how complex system, no matter what's going on, that there are going to be planetary objects around it. Pretty much all cases. And that's the death knell, of course, for the Wolfson model of freak planetary system formation, and is support for the model we now know and love, which has been refined over the years because of all the oddities we've found. Now, it's a really interesting story, but it goes way back before that. We've got a long history of the things that led to finding the first planets. Well, we take it a bit for granted now. We're finding so many planets, and I have the good fortune of getting to be involved peripherally in some of the discoveries. I've had the very entertaining job of killing some planetary systems, so it should be said that the number you gave at the start can go down as well as going up.
Oh, I didn't know that.
Some of the planets that get confirmed later on get redacted, get killed, and I've probably... Certainly as lead author, I've never led a planet discovery, but I've been involved with them. But I've led a number of research projects that killed planets that other people claimed. So I've probably been net responsible as an individual for a negative number of planet discoveries. That can happen, but it's really important that we do that kind of work. I've always been really passionate about that, because all of the things that we do to talk about how common planets are, to look into how they form, and further down the line to try and find planets that could be like the Earth and to try and look for life on them. All of that is based on the catalogue of the known. What do we know? What's the variety? And so if you've got planets that are in that catalogue that don't exist, they're polluting that catalogue and confusing and obscuring the truth. So it's really important to not just accept that when a planet is claimed and marked as confirmed, that's the end of the story, but we need to follow it up and say, does it make sense? Could there be something else going on? And in those cases, we do learn more about it. So it's a fascinating field. I'm really fortunate to have gone from being a kid who wondered to an adult who gets to be involved in the process. That's incredibly wonderful for me. But it's a fabulous story, and we have lived through a great scientific revolution, in many ways one that's as big as the acceptance of continental drift, or the origin of species and Darwin, or general relativity and Einstein. It's one of those revolutions, and when you talk about the other ones, you think about how epochal and incredible and how they changed the world, and we've just lived through one. It's amazing.
Yeah, it's incredible. And will it never end? I mean, the thought of looking up into the night sky and seeing billions of stars and knowing that there are probably multi-billions of planets is just, it's mind-blowing.
And the rest. I mean, to me, it's a numbers game, and we talk about this when we talk about life elsewhere, but the numbers get ridiculous really, really quickly. Now, we've been heavily biasing what we found to finding planets closer to their stars than the Earth is to the Sun. The overwhelming majority of planets we found are very close in, but there will be planets further out as well. You're not going to have a situation very often where you've got a few planets near the star and nothing further out. So a lot of the very tentative estimates you get of the number of planets in the universe say, well, imagine there's just one planet per star. Based on what we've found so far, I think it's fairer to say there are probably nearer to 10 planets per star. And depending on whether Jared Isaacson, the guy who's taken over NASA, who is not an astronomer, gets his way and restores Pluto, if he restores Pluto, then you have to argue that Ceres, Makemake, Haumea, Eris, all these other things are planets in the solar system. You could have 20 planets in the solar system. So let's assume 10 per star. Whether Pluto is or isn't, leave that for a side. I have strong opinions on that. Other opinions are available. They're wrong, but they're available, as Matt Commode always says. Yes. Ignoring that, though, if you assume 10 planets per star, because it's going to be nearer to 10 than one, and astronomers work in factors of 10, in our galaxy alone, we have somewhere around 400,000 million stars. Now, that number also is only accurate to a factor of 2 or 3, so it could be 200, it could be 600. But call it 400,000 million stars. That means 10 planets per star, you'd have 4 trillion planets in our galaxy, ignoring the free-floating ones that don't have a star to call their own. 4 trillion planets in our galaxy. There are more galaxies in the observable universe than there are stars in our galaxy, by orders of magnitude, which means you start getting to the point which, in the observable universe alone, ignoring the part of the universe that we can't see because that's utterly unquantifiable, but just in the part we can see, you'll have planets numbered in the sextillions or septillions. So a trillion is 10 to the 12, a trillion is 1,000 billion, a quadrillion is 10 to the 15, which is 1,000 trillion, and so on. So these numbers are utterly, astonishingly, overwhelmingly mind-boggling. And that's where I come to with this thing that if we're the only place with life in the universe, then there's something very unusual going on.
Absolutely, yeah. And what was it? It was the movie Contact, where they said space is really big. So if it's just us, it seems like an awful waste of space.
It is. I mean,
I always like that line.
Yeah, well, the question of life elsewhere is one that really polarizes people. I mean, everybody's interested to know the answer. Arthur C. Clarke said something along the lines of there are 2 possibilities. Either we're alone in the universe or we're not. Both are equally terrifying. A lot of people, Stephen Hawking was very adamantly we shouldn't try and contact aliens because they will kill us in the face. I don't tend to agree with him. No. But it's one of those discussions that really fires people up, gets people energized. And for me, it would be actually far more terrifying to know we're alone in the universe, because that means life is such an impossible fluke that given planets numbering in the sextillions or septillions in the known universe, we're the only one with life. Which means that only one planet in 10 followed by 20 zeros or more gets life on it. And that seems infeasible to me. But we won't really know until we move forward and we actually proceed with the search for life elsewhere. And as I've said in a previous episode, absence of evidence is not evidence of absence. So if we find life, then we'll know we're not alone. We'll know that life's common in the universe. The longer it takes us to find life doesn't mean that there is nothing to be found. It just means that life is scarcer, basically. So the longer we take to find it, the better we'll get at doing it, the further we'll be able to look, the more planets we can sample, and that will then give us a handle for the commonality of life. So if we find life in our lifetime, all well and good. If we're still looking in 1,000 years, I'd be gobsmacked. But that just tells you life is a lot rarer than we thought.
Indeed. And we'll talk about that more in another special episode when we do part 2 of astrobiology. We kind of we didn't have enough time to talk about it last time, so we're going to do a part 2. But
I talk too much.
It's also an area that makes your brain hurt. So we decided to, give it a miss this week and go back next week. So where do you want to go with this? Like everyone knows there's exoplanets. Everyone knows there are powder puff planets, and they've actually got names for them.
We've got some
looked up.
named.
So, we can officially say that as far as planets are concerned, we have specific types of planets in our solar system, and that is rocky planets, gas giants, and if you for want of a better term, ice giants. But in the exoplanet world, there are several other types. You've got Neptunian-like planets, super Earths. You've got hot Jupiters. You've got super cold worlds. You've got pulsar planets, and there's even circumbinary planets where they're orbiting 2 stars. We don't have that, thankfully. That could be messy, especially when it comes to trying to predict the tides. But it's there's so much more going on out there.
There is, and it reflects something that's incredibly human. And it again goes back to that discussion about Pluto and many other things in human experience. What we find in every field of study, but in astronomy in particular, is you have a continuum of things. You've got from the very small to the very big with no obvious sharp gaps. You'll find everything in planetary systems from stuff the size of a grain of dust to things more massive than the sun, depending on the planetary system you're in. What we tend to do as humans is we tend to break down that which we see as a continuum into manageable bite-sized chunks by grouping like with like in order that we can then better study objects. And so, for example, you'd say that the Earth is more like Venus or Mars than it is like Jupiter, so you categorize them into different subgroups. For humans, we do this all around the world. You've got babies and toddlers, children, teenagers, adults, retirees, pensioners. And you set boundaries, and those boundaries don't always agree from country to country. You remember the incredible day that you suddenly wake up and you're able to drive legally when the day before you weren't. And fundamentally, you've not changed as a human. You're one day older out of several thousand days at that point, about 5,000, 6,000 days. But miraculously, you've crossed this arbitrary threshold, which we've put there to separate people who can't drive and people who can but maybe shouldn't. That's kind of where the division is. Yes. We do this as humans all the time to categorize things, and that's kind of where Pluto fell afoul. And it's where all these groups of different types of planets come from. You've got hot Jupiters and warm Jupiters, super puff planets, and all sorts of quirky things. And those terms are taking the broad spectrum of planets that we've got and trying to group apples with apples and oranges with oranges, things that are similar to one another. And the diversity just continues to astound us. Every time we think we've found the most extreme of whatever, we find something that's even more so. Like I said, we found planets who we can calculate their size by how much light of their star they block. We can calculate their mass by how much they pull their star around. We've got a subset of stars and planets where we can do both those things, which lets us figure out the density. And from them, we found planets that are less dense than cotton candy, which are the super puffs, fluffy ones, probably coming towards the end of their lives because they're so low density that they are probably being stripped away by their star's stellar winds. We found planets that are effectively like comets, with tails as their atmosphere stripped off. I mean, to some degree, actually, the planet Mercury in the solar system is a comet. It's got a beautiful long sodium tail. And one of my favourite astrophotos I've ever seen is a picture of Mercury near the Pleiades, where somebody's done some imaging in a sodium filter, and you can see Mercury's tail visible on the image. It's an astonishing thing. So we found planets like comets. We've even found planets around pulsars, and they were the first 3 planets we found around other stars. They were Phoebe-Tau, Poltergeist, and Rao, these stars orbiting a pulsar named after 3 kinds of the undead. So there's this huge variety there. It's worth mentioning, actually, from the names. The names are being allocated by the International Astronomical Union, just as names of asteroids and names of satellites and things like that are. What they're trying to do with them is to be very democratic globally, to try and represent multiple cultures rather than just have all the planets draw from a single cultural base, a single kind of background. And so they've been running a series of competitions over the years for the general public, where a given planetary system is given to a given country. And then people from that country get to nominate names, and then people from that country get to vote on it. And I think we've now got more than 100 planets named. We've had a few of them from Australia named, and I'm actually just trying to look up the planet names from the IAU. They're the official ones. Now, what's interesting is these are official names. They're the IAU's official names. I, therefore, try to use them in my papers. And I've had pushback from astronomers because everyone's so used to the catalogue numbers. So what I've been trying to do is you give both names, you give the catalogue name and the proper name. And I think where it will go long term is it'll become a bit like comets. You know, I've been trying to get images through the cloud and cursing the weather of Comet Pan-STARRS at the minute. And we talk about Comet Pan-STARRS, but its real name that I'd write down if I'm writing it is C/2026R3 brackets Pan-STARRS. And I think in the long term, I can see exoplanet names going that kind of way once people get used to it. So 51 Pegasi B, for example, is Dimidium. That's the name that's been given there. And you can use both interchangeably, but because astronomers are used to 51 Pegasi B, that's where it sticks. Now, the names come from lots of different cultures. They come from lots of different groups. There are planets that have been discovered by Australians that are named after Australians. There are planets that are named after people. You know, you've got the planet Galileo going around 55 Cancri. So 55 Cancri's 5 named planets are all named after astronomers. You've got Galileo, Brahe, Lippershey, Janssen, Harriot, and that's it. So 5 planets, 5 names. Lots of different names from different cultures. We've got names that are controversial, names from different folklores, names from different cultures all around. And that list is growing, but you don't see it used all that much yet because a planet needs to be confirmed and then very confidently there and well studied for it to get onto the list for the names. So I think, like I say, we've got a bit more than 100 names and a bit more than 6,000 planets. Those 6,000 planets, that number will go up as well as down, but it's not going to be too long until we're 10,000 plus.
Yeah, I figured out why some of these, sometimes the number goes down. They're the ones that have been discovered by Monty Python. It's a planet. No, it's not. No, it's not. So that's why.
We'll also lose some with Gaia. So Gaia has been this amazing satellite measuring positions of stars, and it can measure the wobble on the sky, side to side of stars as a result of their planets. Now, historically, by far the two most successful methods of finding planets are the radial velocity method, where we measure the star's speed towards or away from us and see it wobbling along the line of sight, and the transit method, where we see it pass between us and the star, and that means the orbit is edge on to us. But for those radial velocity planets, we're measuring the fraction of the wobble towards or away from the observer. And the orbit could be tilted almost edge on or almost face on to give that same amount of wobble along our line of sight. Gaia will give us the other dimension. It'll give us a side-by-side, which means it'll find us the tilts of all those planets. Some of those planets will be on orbits very tilted to ours, and therefore the mass that they have will be much higher than that we think they probably have. And that there'll be a certain amount of attrition where planets that we think are planets are actually brown dwarfs. And that is another of these arbitrary boundaries, which we set roughly at 13 Jupiter masses. But we will have planets falling off at the top end when Gaia comes out. I suspect you won't see the number drop, though, because Gaia will also lead to so many new discoveries that will overwhelm the ones that fall off the top end.
Yes, that's a fair point. So it's got to be one of those waveforms that goes up and down as situations change. Yeah. Let's take a go on.
I was going to say I've been responsible for a number of systems getting killed because people proposed planets in places that they seemed unlikely and they didn't make sense from an orbital mechanics point of view. So I ran simulations and showed that if these planetary systems are real, we're seeing them in the last 10 years of a 4 billion year lifetime before the planets crash into each other or reject each other, and that's not feasible. So there must be something else going on. So on the one hand, boo-hoo, you've killed a planet. That's not good, you naughty boy. On the flip side, though, it's really cool because there's something there creating the signal that people have measured, and it isn't planets. So what is it? So science always gives you more questions.
Indeed it does. And you're listening to Space Nuts with Andrew Dunkley. I do know my name. And Professor Jonty Horner. Let's take a short break from the show to tell you about our sponsor, NordVPN. Let's talk about your online security. Now, I can tell you from personal experience, last year when Judy and I were overseas, we ran into a bit of a frustrating issue. There were certain apps we simply couldn't use without a VPN connection, things like our banking apps. They wouldn't load, and even a sports app I rely on wouldn't let me watch games back home because of geofencing and things like that. So with NordVPN, I was able to watch football back home while crossing the Atlantic Ocean. It was pretty weird, but it worked. And NordVPN is the best in the business. With NordVPN, you can securely connect to servers all around the world, which means your apps think you're right back home, even when you're not. It also encrypts your internet traffic, hides your IP address, and keeps your personal data safe from hackers and trackers and anybody else who's trying to get at you online. And this can happen in public Wi-Fi situations, in hotels, airports, cafes, anywhere like that. The best part, it's fast. Thousands of servers globally, and their NordLynx technology allows you to run seamlessly. No slowing down. It is brilliant. Right now, you can grab the special Space Nuts deal through this URL, nordvpn.com/spacenuts. You'll get 4 extra months free plus a 30-day money-back guarantee. So there's absolutely no risk if you want to give it a go. That's nordvpn.com/spacenuts. Stay safe online with our sponsor, NordVPN.
Roger, you're loud and clear here also.
Space Nuts.
I'm going to have to write it down so I can read it properly. Jonty, where do you want to go next? I mean, we've found so many. I don't think we will ever stop finding exoplanets because as technology improves, they're just going to keep stacking up, aren't they?
Yeah, I mean, if we talk about the 6,000-ish we found so far, 6,278, I think it was, we said earlier on there are probably 4 trillion, give or take, in our galaxy, which means we've only found about 1 planet for every billion planets that are in our galaxy. We've barely scratched the surface. In doing that, we've utterly revolutionized our knowledge of the variety of planets that'll be out there, of how planets form. We have still, for me, not found something truly Earth-like. I think that's the next hurdle. Now, you'll see a number of media articles over the years saying the most Earth-like planet yet has been found. All the bloody...
I actually read an article yesterday which said, Super Earth found potential life, da-da-da-da-da, and I thought, yeah, here we go again. And I read it, and of course, when you get down to the second last paragraph, it says, of course, there's no confirmation that this is even a rocky planet, but...
Yeah. And to me, it's like imagining that you're an alien visiting the Earth and you're flying over the oceans and you say, we found the most human-like animal yet. It's about 2 meters long. It's a couple of 100 kilos, 100 kilos. I mean, it's a dolphin. It's nothing like humans, but, it's that kind of thing. And I think I understand the urge for scientists to talk about things in the context of the habitable zone in the papers because that's interesting. Is it too warm? Yeah. Is it too cold? I understand the thing of saying this planet has similarities to the Earth. It's about the same size, or it would be about the same temperature. What tends to happen, though, then is that the press release from the universities gets a little bit more hyperbolic in it because they want to get the reads and the clicks, want to get the word out there. It then gets into the media who, again, are being more hyperbolic. And we're seeing it at the minute with the articles about the meteor shower that's active at the minute, where people are building it up and blowing it up to a level that is not practical and not observable and leads to disappointment. It's not helped by the fact that there are people who are making careers out of discussing how Earth-like planets are that they didn't discover, that they weren't involved with, to get themselves clicked and to get money. And a lot of the beautiful visuals you get cropping up online about Earth-like planets come from one resource, which is called the Planetary Habitability Laboratory in Puerto Rico, which has been an ongoing source of frustration for me and colleagues, because there's been stories that people I know have published about planets, and then this entity puts out their own press release saying, we've calculated this magic number and this is the most Earth-like planet found and it's probably got life. And the scientists who discovered it have said none of those things.
Yeah.
And all the coverage is, look at this beautiful AI-generated artwork. Isn't this amazing? So I do, I had a fun story about this a few months ago. I had an author get in touch with me asking me to proofread a chapter of a book that they're doing. And they'd got a little bit in there about all the potentially Earth-like habitable planets that have been found out there. And they use that as a resource. And I had to back them off on it and say, look, it's brilliant to talk about this, please don't use this as a resource. If you use their equations, Venus would be the most habitable planet we've discovered other than the Earth. And I certainly wouldn't want to have a holiday there.
No. You'd need 20 gazillion plus sunscreen for starters, or something like that. Now that'd be Mercury, but it's impossible.
Unless we
It's an
built Cloud
impossible
City,
place.
and we could live among the clouds. That'd be a bit different. But yeah, there's a lot of stuff around it, and we've talked before about other things. We talked about interstellar comets and the obfuscation of science when it comes to those, and they definitely are not aliens. And I'll say again, they definitely are not aliens. In this case, the exo-Earth fatigue is real. People in the general public are convinced that we found planets like the Earth already. And I mean, it's great. It keeps people interested, but it also diminishes the impact when we finally do. Astronomers will finally find a planet that could genuinely be truly Earth-like. We'll then need to do a lot of work to characterize it. But you can imagine in 10 years' time, we get data back from a planet that shows not only that it could be Earth-like, but the surface temperature is right and that there is liquid water in the atmosphere. And the scientific community will be, wow, this is our best discovery ever. This is so cool. And nobody will care because, well, you've done it 10 times already. The media told me so.
Yeah. Actually, I think I've found it. A potentially habitable new planet has been discovered 146 light years away. But then it goes on to say, but it might be minus 70 degrees Celsius. But there's a story like that coming out every other week.
And if you want to play that game, our definitions of habitability are based very much, as we talked about in the previous episode, on our understanding of where Earth life could thrive. And in the solar system, we've got potentially habitable worlds all over the place. Mars is potentially habitable on the borderline. Depending on what you think about bacteria in the atmosphere, Venus could be habitable for that type of life. We've got all the icy objects with buried subsurface oceans that are habitable but not detectably habitable because there's ice in the way. I don't think it benefits people to overplay these discoveries, even though I fully understand the reason why people do. And I don't think it does anybody a service long term. It is the unfortunate reality of what it is. But hey, people are interested, of course you'll play to that. In the kind of modern media cycle, nobody remembers the retraction. They all remember the discovery, Everybody remembers cold fusion. Back from when I was a kid and a teenager. That was, of course, published in the Journal of Irreproducible Results, otherwise known as Nature. These things happen.
Yeah, they do. So, all right, where to next with exoplanets? With so many discovered, that's provided a baseline for the probability that every star has at least 10 planets around it.
We're finding them in a growing variety of ways. It's instructive a little bit to look back at history. If I took you back to the early 1800s, our telescopes had finally got good enough to measure the motion of nearby stars against the background stars. That allowed us to start measuring the distance to nearby stars using trigonometric parallax, where you look at a star from one side of the Earth's orbit, then the other, and see it move against the background, just like your finger moves if you look from one eye or the other. That same trick. At that time, people started measuring it, and they realized that nearby stars also moved through space. They were undergoing what we now know as proper motion, moving against the background stars in a straight line, which is their true space movement through the galaxy as seen by people on Earth. A guy called Friedrich Wilhelm Bessel, who was a fabulous astronomer in the early 1800s, was doing observations of Sirius, which is one of our closest star systems. It's our brightest star in the night sky. And he found that once you took away the parallax motion, the wobble left and right because of the Earth going around the sun, that Sirius was wobbling as it moved across the night sky, and it looked as though it was being pulled around by something as massive as the sun. But you could see nothing there. There obviously was something there pulling it around, and it turns out that was the indirect discovery of what we now know as Sirius B, the white dwarf star. It wasn't the first white dwarf to be found, but in this case it was discovered indirectly. We saw Sirius doing something unexpected, we saw it wobbling, and we used that to infer the presence of the white dwarf star around it. And of course we got another example of this a little bit later in the 1800s with the discovery of Neptune, not through direct observation, but initially through mathematics, through John Couch-Adams and Urban Le Verrier doing calculations of how Uranus was moving across the sky, seeing that it was moving as though something we couldn't see was pulling on it, predicting where that thing would be, and Neptune was duly found. So they set this heritage of inferring the presence of something we cannot see because of its effect on something else. And that has been foundational to how we find planets around other stars. That's fundamentally how, for more than 99% of them, we've discovered them. There have been slip-ups on the way. In the 1940s, 1950s, Edwin van der Kamp, who was director of Sproul Observatory, thought he'd found planets around Barnard's star, which is the star with the biggest proper motion in the sky. Turned out that he'd actually discovered the cleaner, because what was happening was that his telescope was getting dirty. He used a lens telescope, a refracting telescope. As the front objective lens got grottier, the way in which it bent red light compared to blue light changed, causing Barnard's star position to shift against the background stars. And when it got cleaned, it all went back to normal. He went, very sad, but he went to his grave in the 70s, convinced he was a victim of an injustice and he'd found planets around Barnard's star. We now have found planets around Barnard's star, but they're very different to the ones he proposed. We also had the fabulous story, just prior to the pulsar planets actually being found, the same researchers thought they'd found a planet around a different pulsar and announced it at a conference, and someone went away and said something a bit odd about this. What had been done was they were measuring the timing of the pulsars. So pulsars are super condensed neutron stars, leftovers from the explosion of a star as a supernova, which have a couple of magnetic hotspots on their surface. And as they spin, they beam radio waves into space like lighthouse beams. And when the beam sweeps across us, we get pulses of radio waves like the ticking of a clock.
Yep.
With this pulsar,
they're very precise, aren't they?
Yeah, they're viewed as being the most accurate clocks in the universe, aside from when they have the odd glitch or something. And I've had plenty of watchers that do that. In this case, so he was observing this pulsar, and sometimes the pulsars arrived a little early, sometimes they arrived a little late, and this was happening periodically. So ruled everything else out. There must be something causing the distance between the pulsar and the solar system to vary periodically. Ergo, it must be a planet. Turned out that after the conference, someone said, there's something a little bit odd here. Maybe you should just do a double check before you publish it. Went away and found a single typo in their code that meant they didn't properly account for the motion of the Earth around the sun. So they had discovered a planet, but they discovered that the one that they were stood on, they discovered the Earth. Which, I mean, it's a fabulous discovery. Now, we laugh about this, but it shows how hard these observations are. Finding planets around other stars is incredibly difficult. We've had the wherewithal to understand the methods that we would use for a couple of 100 years. But it was only in the 90s that it really became feasible to do them. And in those early days in particular, there were two methods that hugely dominated. For the first probably 10 years, 12 years of the exoplanet era, the main way we found planets was what you call the radial velocity technique, the wobble technique, which is using the Doppler effect, and you see a distant star, and we can measure its light, and we can break that light to its component colours, seeing what we call the Fraunhofer lines littered across it, which are dark lines that are the chemical fingerprint of what the star's made of. And we can measure their positions in the lab incredibly precisely, and if the star's moving towards us, its light gets a bit blue shifted, and all those lines move a little bit to the blue, and if it's moving away from us, they move a little bit to the red, and if you can monitor it for long enough, you can see the star coming backward and forward. It's wobbling, you can infer the presence of something massive pulling it round. You can figure out the orbital distance of that object by how long it takes for the wobble. So it comes towards us, goes away, comes towards us again as it does one full lap. That gives you the orbital period. You can infer the mass based on the size of the wobble, but we're only measuring that component along our line of sight. So you get a minimum mass that it could be, and it could be higher than that. So we can learn about the orbit. That's the radial velocity technique, and that is an indirect method. You see the star wobbling and infer the presence of a planet or planets around it. The technique that's taken over from it is the transit technique. That's where a planet's going around its star and its orbit's just lined up right that every time it goes around, it blocks a bit of the star's light. The star dims and then brightens again periodically. And by measuring the periodic dimming, you can infer the presence of something blocking the star's light. Again, that gives you the orbital period because you get one dip per orbit. And it gives you the size, the diameter of the planet, because a bigger planet will block more light. But fundamentally, again, it's an indirect method. You see a star doing something odd and infer the presence of a planet. Now, both these methods were known and were used for hundreds of years. We saw binary stars being observed because of the dimming during the eclipses. John Goodricke, a British astronomer who died at a very young age, explained Algol, the winking demon star, as being a binary star back in the early 1700s. That is effectively the same as a transit technique. It's just you've got a bigger blocker. Problem is, our eyes are only sensitive to variations in light at about the 20% level. Smaller variations than that, we just don't pick up. Your lights can be flickering by 20% and you'll barely notice it. For a binary star, the brightness can change by a factor of 2 or more. For an exoplanet, Jupiter blocks about 1% of the light from the sun. That is just something you cannot see with the naked eye. So to be able to use the transit technique, we had to wait for detectors that were sensitive enough to measure incredibly fine variations in brightness to come along, which is why we've only been able to use the transit technique this millennium. It wasn't really possible before that. Similarly with the radial velocity technique, we could measure the wobble of stars from binary stars for decades because the movement of the lines was sufficiently big, you could measure it on a photographic plate, and you could measure speeds of kilometres per second fairly easy. Yep. Planets like Jupiter going around the sun cause wobbles that are measured in metres per second, maybe 10 metres per second. That is, again, such a small wobble that taking photos on photographic plates of the spectral lines, the resolution isn't good enough. Our spectrograph we've got up at Mount Kent in our facility Minerva Australis, typically the measurements we're making are measurements of a thousandth of a pixel shift in a given line. And the only way we can do that is because you're seeing thousands of lines at once, and you can work out statistically what they're doing. So even with the most modern cameras and most modern technology, it's still hard. And that's why even though we had the wherewithal to understand the physics and to know how to do the techniques 200 years ago, we were stuck in a technology gap. We just had to wait for the technology to reach the right place. And that's why finding the first was hard. But once you found one, you'll find 10, you'll find 100, you'll find 1,000. I'd point people, incidentally, to the astonishingly beautiful videos by System Sounds in partnership with NASA that were put out to celebrate the 4,000th and 5,000th discovered exoplanets, where they run the discoveries over time on a map of the sky where the discoveries are marked with a little ring. And every planet gets its own musical note, where the musical note tells you the orbital period of that planet around the star. So a high-pitched note like a ding will be a planet really close and going around really quick, and a low-pitched note like a ding, that'll be a planet a long, long way away going around really slowly. And it shows you the diversity we found, but it also shows you this incredibly accelerating rate at which we're getting better at doing it, because now we've crossed that threshold where the technology wasn't good enough. And now the technology keeps getting better. We get better at doing it, and the numbers continue to rise. And depending who you talk to, there are people who suggest we'll certainly cross the 10,000 count by 2030. Might not be long after that before we cross the 100,000 mark. That will all depend on Gaia, but also the Nancy Grace Roman telescope that's due to launch in a few years' time.
Yeah, it's going to be amazing, and who knows what we will find. And we'll talk about a bit more in a moment here on Space Nuts.
3, 2, 1.
Space Nuts.
And you're with Andrew Dunkley and Professor Jonty Horner. We're talking exoplanets on this special episode. It's our last segment, so over to you, Jonty. Where do you want to go to finish off this particularly interesting topic?
Well, I think it's also worth flagging out the diversity of places that are doing this work as well. I mean, amateur astronomers are contributing a huge amount. We're now at the point where the technology's moved on enough that you can observe and measure exoplanet transits using a fairly cheap off-the-shelf telescope. Many amateur astronomers will occasionally observe the transit of one of our bright planets. There was an article on Australia's ABC News recently about some amateur astronomers who banded together to be involved in planet discovery. I'm increasingly proud of the facility we've got at UniSQ, which is, as far as we know, the only dedicated Southern Hemisphere exoplanet observatory in the Southern Hemisphere. There's a lot of facilities looking for them, but we've got our own facility at Mount Kent Observatory just outside Toowoomba that all it does is look for planets and learn more about them. It doesn't split its time with other tasks. Its job is planet search. And it's really important to stress that, particularly for the younger listeners from Australia, there's this perception that the only place you can go to do real science and to become a scientist is to go to the big cities, the big capital cities, to the Group of 8 universities. And for people in regional Australia, and particularly people from less prestigious backgrounds, lower socioeconomic backgrounds, all the rest of it, there's this very much feeling that it's a big city thing and you've got to go to the right schools. But we're at a small regional university in regional Australia, and we're leading the world in this. You know, we have two of my colleagues, Professor George Zhao and Associate Professor Chelsea Huang, are between them responsible for 30% of all time Australia has ever had allocated on the James Webb Space Telescope. And they've used that to study planets around other stars. So I do want to stress to people listening that this is not just something that's done in the US, or it's not just something that's done at the world's top 10 universities. It's something that you can participate in yourself. There's some fabulous citizen science programs out there. And there is going to be an increasing extreme wealth of data coming out in the coming years that astronomers simply won't have enough hands to go through. So I'm sure that if people keep their eyes out, there will be other citizen science programs pop up in the coming years. You know, currently I'm looking at the wonderful NASA Exoplanet archive here, looking at the different methods planets have been discovered by. And we've now got, I think it's 11 different methods that have been used. Of our 6,283 planets, 4,640 have been found by the transit method. That's overwhelmingly the most successful now. And that's because you can play a numbers game. You can look at thousands of stars at once, looking to see if any of them wink. And that's what the Kepler spacecraft and more recently NASA's TESS spacecraft did. We've got nearly 1,200 planets found with the radial velocity method, the wobbled method. Now, should be said, this is a discovery method, and a lot of these planets have then been studied using other methods, but this is how they were found. So between those two, we're at, 5,800. Of the known planets, 6,200 were found by those. That's 90-odd%. Yeah. Of the remainder, we know of 278 planets that were found by microlensing. This is where you look at very distant stars like the middle of the galaxy and look for planets and stars that we can't see passing along our line of sight and their mass bending light to cause that background star to brighten then fade. Very small number found so far, but the Nancy Grace Roman telescope will likely discover thousands, if not tens of thousands of microlensing planets in the coming years, because that telescope's going to go and stare at the middle of the galaxy, among other things, and should be very useful at that. We've got nearly 100 planets now discovered by direct imaging. And they're really interesting because they're the ones where we actually see the planet, and we find it by seeing the light from the planet. So it's amazing that we're nearly at 100 there. And my favourite movie of all time is really the movie of the planets orbiting the star HR 8799, where observations spanning more than a decade now have been made where you can see 4 planets around that star and watch them move in their orbits. And you think, from where we were when I was a kid, where we didn't even know if there were any planets out there, we can now watch some of them go around their stars in real time. Yeah. That's just astonishing. There's a lot of other really niche methods that have been used, but they're kind of the big 4, I'd say. And I think the one that's going to grow over the coming decade more than any other is astrometry. So at the minute, there is a grand total of 6 planets that have been discovered by astrometry. This is measuring the positions of stars in the sky and seeing them wobble side to side. It's what Bessel did with Sirius to find Sirius B. We've only found 6 so far, but the Gaia spacecraft observed for a long time, finished observing, but we're still getting new data releases from it. Gaia data release number 4 is coming allegedly in December this year, maybe pushed back a little bit. But that's where they will have enough quality and analysis of the data and enough time period the data covers to start finding planets in the Gaia data doing astrometry. And people are still predicting that could yield tens of thousands of planets. Even if you're a pessimist, it's easy that Gaia could take over from Kepler and TESS as a tool that found the most planets. That's just in the next year or two. And what we're doing then, we're finding more, but where we're shifting to is not just finding them, but learning more about them, characterizing them. And that's where the future of exoplanet science is. It's not just enough now to find a planet. We want to learn more about it. What's its atmosphere made of? What's its internal composition? What's it like? That's where we're going. And we're making great leaps in that. We are finding out what chemical species are in the atmospheres of different planets. Currently only really doing it for the very biggest ones because they're the easiest to observe. But that's very much the future, and that's what will lead to the search for life elsewhere, which I think is what really hooks a lot of people into the subject.
Yeah, it's fascinating. For the record, the first actual photograph of an exoplanet was in 2004, and it was 2M1207b.
Yes.
Which apparently is an exoplanet orbiting a gas giant.
Yes.
which is a big one, about 5 times the mass of Jupiter. So, so that was the first one ever photographed that we actually got to see a picture of rather than just
Absolutely.
identified through some...
I mean, we're still just seeing them as a single pixel. We're not
Yeah.
going to be at the point of Star Trek type images of the surface for a long, long, long time because the resolution's a challenge there. But that was a breathtaking thing. And it is worth noting that the overwhelming majority of the direct imaging planets that we've imaged are massive and young. And the thing about them being young is they're still hotter, which means they glow brighter and therefore are easier to see.
Okay. Last chance to talk about exoplanets. We're going to wrap it up in a sec. Any final comments?
Well, I think there is so much more we could talk about. I mean, like every topic we get onto, I talk too much, but we could fill several hours worth of excitement digging into the nitty gritty. But I think the thing that leaps out to me, probably even more than the ubiquity of planets, the fact that they're everywhere, is the diversity. You know, when I was growing up, we thought that there would be other planetary systems, but we weren't sure. But we assumed they'd be like the solar system, you know, rocky planets on the interior, giant planets on the outside.
Yeah.
And the first planets discovered shattered that. You had planets around a pulsar, which makes no sense. We think they were probably a second generation of planets. The initial planets there were destroyed and new ones formed after the supernova, but we're not sure. You then found a hot Jupiter, a planet the size of Jupiter, going around a star like the sun every few days. And that was enough to revolutionize our understanding of how planetary systems form. And with every new technique and with every new facility and with every new way of finding planets, we find planets that are more different to the solar system than we could ever possibly imagine. The lightest, well, not the lightest, the fluffiest planets, the lowest density planets, are so fluffy that they're being torn apart by their stars. We mentioned them early on. The highest density of any planet in the exoplanet catalogue is denser than any metal or mineral or anything known on Earth by such a large distance that there is speculation that it could be a fragment of a white dwarf or something, that it could be actually not a lump of iron, but a lump of white dwarf material or something. We just don't know. And everything in between. We're finding that the planets in our solar system are pretty average. We still don't have a handle on how common are planets like the Earth, how common are planets like the Earth on Earth-like orbits. We also don't really have a handle yet on how common are planets like Jupiter and Saturn. In other words, cold Jupiters, planets that take a decade or more to orbit their star. Because finding them's hard. You need to watch for a long time. So we know much more about planets close in and planets very different to our own than we do about planetary systems similar to the solar system. So I think one of the big questions now is not is the solar system unique, but rather how unusual or usual is the solar system? Are planetary systems like our one common, or are we a bit of an exception? We're not really in a position to answer that yet. It seems that the frequency of Jupiter-like planets around other stars is somewhere between 5 and 20%. And by Jupiter-like, I mean Jupiter mass on a Jupiter-like orbit around stars like the sun. But that's a big variety of, possibilities. We just don't know yet. And so even though we now know that planets are everywhere, we've barely scratched the surface. And it's the kind of thing where if we had this chat again in 5 years' time, the numbers would be different, but there would be whole swathes of new knowledge then that we can't even predict now. There will be things that surprise us just as much in the years to come as hot Jupiters and pulsar planets did at the dawn of the era. And that's part of the fun.
Yeah, and there'll probably be planets we can't even imagine that would be discovered that we couldn't have even contemplated existing. And I can't even pretend to make one up at the moment, but there will be. Of course, the search, as you mentioned, is for an Earth-like planet, a rocky planet in the right place, orbiting a star like ours, that basically duplicates Earth. We just haven't found one of those yet, have we?
No. No, with a caveat. We may have done and it have not been picked up. There's more to learn about these things. I still think of the planets we've found so far, Venus is more like the Earth than anything we've found so far. I also think, though, that that's even a difficult question, because what do we mean by it being like the Earth? If you went and looked at the solar system 4 billion years ago, I don't think you'd have considered the Earth an Earth-like planet. It would have had this incredibly thick atmosphere, very different to ours, with a very different composition. It would have been outside the edge of the habitable zone because the sun was that much fainter, but it would probably still have liquid water on the surface because it had such an intense greenhouse effect. So there could almost be a philosophical question about how long would you consider the Earth to have been an Earth-like planet?
That's a really good point. Yeah, and there's the possibility that we have observed planets that just aren't where we are yet because of the time difference in the travel time of our vision. So again, it mightn't be there yet, and it could be billions of years before it is, and we won't be around to confirm it. There's all sorts of weirdisms that go into this. The bottom line for me is if they find one, it's got to have kangaroos on it. Otherwise, there's just no Earth-like planets.
Oh, absolutely. I mean, it would be very interesting to imagine kangaroos in space. I talk a lot about the Dragonfly mission going to Titan and the fact that Titan is the only other body we know of with permanent liquid water on the surface. Well, not permanent liquid water, permanent liquid on the surface. The water there is harder than granite, frozen solid, but it's got liquid methane and ethane there. But on Titan, unlike on Earth, you could fly under your own power. If you strapped a pair of wings on, the gravity is low enough and the atmosphere dense enough that you could flap around and soar. I have never thought about how a kangaroo would react if you took it to Titan.
It would just launch itself.
Just launch itself. It would, of course, need a very, very good spacesuit because it's so cold there, and kangaroos are not fans of the cold. But yeah, that would be the shock. If Dragonfly hops around, flying around on the surface of Titan and then gets attacked by a kangaroo when it comes into land, like we see some of the videos online of kangaroos being territorial, that would be the most bizarre discovery of life elsewhere that I think I could imagine. Kangaroos on Titan.
I wait with bated breath. Although kangaroos do have one particular problem in this country. They do not know how to get out of the way of a car. Even when they do, they go, oh, no, hang on, I want to get back in front of you. Bang. Okay, see ya. Anyway, that's our problem. I'm sure it's the same in other countries with other animals and other planets probably that we're unaware of as yet. Jonty, that's been a lot of fun. It's a fascinating topic, and it's one that will keep evolving, I think is probably the best way to describe it. Thank you so much, and we'll catch you again real soon.
It's a pleasure, and I'll look forward to it.
Professor Jonty Horner from the University of Southern Queensland. And thanks to Hugh in the studio. Couldn't be with us today, made a fatal error. He's back in hospital. He ran into an X and he called his exoplanet. Think about that. It's terrible. And don't forget to visit us online if you dare at spacenutspodcast.com or spacenuts.io. Until next time, thanks for your company. We'll see you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.